This lecture is going to talk about how to find properties. So the first thing I want to talk about is what you need to know in order to find properties. Well, the very first thing to pay attention to is what substance are you talking about. It's critical to make sure you pay attention to what substance you're dealing with. Is it air? Is it nitrogen? Is it water? Is it one of the refrigerants? So pay attention to what the substance is. The next thing to ask yourself is, do you have enough information to fix the state? And usually that means two properties. There's this question of whether the properties are independent or not, but in most cases you need to know two things in order to fix the state. The next thing that you want to concern yourself is making sure you know what phases are present. Are you dealing with a liquid? Are you dealing with a liquid-vapor mixture, or are you dealing with a gas or vapor? Many times, if you find yourself having difficulty finding properties, it's because you've jumped to the wrong conclusion about whether it's a liquid, a mixture, or a vapor. You need to make sure that you figure out which of those three cases you're dealing with before you go into tables looking for properties. So I want to talk about that first. So the issue here is figuring out whether we're dealing with a liquid, a vapor, or a mixture of the two. How do we take the properties that we know and determine which of those three cases we're dealing with? And we're going to be talking about how to do that a little bit later in this video. The next thing I want to talk about is a couple of new definitions, and that is superheat and subcooling. Superheat, or the degrees of superheat, you'll sometimes hear it referred to, is the amount by which the temperature of a superheated vapor is above the saturation temperature. So if we're told that we have a vapor that is superheated by 5 degrees C, let's say, that means that the temperature of that vapor is 5 degrees C above the saturation temperature. It does not mean the temperature is 5, it means it's 5 degrees above saturation. So that's what degrees superheat means. Likewise, degrees of subcooling is the amount by which the temperature of a subcooled or compressed liquid is below the saturation temperature. So if I say that a refrigerant is subcooled by 10 degrees C, it means that its actual temperature is 10 degrees C below the saturation temperature. Next, I want to talk about where we get information for liquid-vapor mixtures. Well, for the purposes of this class, we're primarily going to be finding property data for liquid-vapor mixtures from tabular data, and that's the entire topic of Tutorial 1. So I'm not going to repeat that information here. Tutorial 1 has a lecture that describes how to do this. There are also lots of computer programs and web resources that you can use to find properties for liquid-vapor mixtures and other phases, of course, for a very, very wide variety of substances. Probably one of the best is the National Institute of Standards and Testing website. The source that we're going to be using for superheated vapors is really the same. For the purposes of our class, we're going to be learning how to use tabular data, and that's of course the whole topic of Tutorial 1. But again, there's many web resources and computer programs that are available to find these properties as well. I want to talk in particular about how to determine whether we have a liquid, a mixture, or a superheated vapor. So I want to return back to a TV diagram. So recall this is a plot of temperature versus specific volume. We have a saturated liquid line, saturated vapor line, and I've shown a line of constant pressure on here. So key thing to remember is that the line of constant pressure is horizontal inside the liquid vapor region, and the particular value of temperature that that's at is called the saturation temperature. So that's the saturation temperature that corresponds to this particular pressure. Now, if we're at any temperature lower than this, so if our actual temperature is less than the saturation temperature, then we have what is called a subcooled liquid. So if I give you a pressure and a temperature, you take this pressure and you look up the value of Tsat from the appropriate table, and that will tell you what this number is. If the actual temperature is less than that, that means you're somewhere along this line. And of course that means we have a liquid, and we call that a subcooled liquid. Subcooled because the temperature is less than the saturation temperature. Simply said, the temperature is less than the boiling point. But you have to remember that the value of the saturation temperature depends on the pressure. If we were at a line of constant pressure down here, of course the saturation temperature would be different, and we'd have to look that one up. Now the other way to look at this is on a PV diagram. So remember, we talked about a PV diagram in an earlier lecture as well. Here we have our saturated liquid line, critical point at the top, saturated vapor line. A line of constant temperature on a PV diagram comes vertically down like this, then again straight across the liquid vapor region and swooping down in the vapor region like this. So this value of pressure that corresponds to the flat part in the liquid vapor region is called the saturation pressure. And again, when we learn how to use the tables, we can take this temperature and look up the value of the saturation pressure. Now, if we're given a pressure and a temperature, one approach we could take is take this temperature and look up the saturation pressure that corresponds to it. So let's say this is the temperature that we're at. We go and we look up this, and then we compare that saturation pressure to our actual pressure. If our actual pressure is bigger than the saturation pressure, that means that we must be somewhere along this line, and that tells us we're in the liquid region. If our pressure is actually less than that, then we must be somewhere along here, so we must be in the vapor region. So when we're at a pressure larger than the saturation pressure, in other words, we're somewhere along here, we're said to have a compressed liquid. So P is greater than P sat gives a compressed liquid. Now notice that a subcooled liquid and a compressed liquid, they are exactly the same thing. They both mean that we're in this liquid region here somewhere, and we're not on the saturation line, we're not in the liquid vapor mixture region, we're in the liquid region. So this is a subcooled liquid. It is also a compressed liquid. They mean exactly the same thing. Now, how do we find properties for compressed liquids? Well, we have two options available to us. The best option, the most accurate option, is to use special tables that are constructed for subcooled or compressed liquid. And the example of that you have in your textbook is table A5. Another option that we use a lot of the time is to use saturated liquid properties at the same temperature. So it's very important to realize that it's the temperature that we need to pay attention to if we're going to use this second option. So when we do this, we're taking advantage of a characteristic of properties in the liquid region that I want to show you. So this second option essentially amounts to saying that the specific volume, for example, of a compressed liquid is approximately equal to the specific volume of the saturated liquid. So when we say use saturated liquid properties, it means use VF, UF, HF, etc. The values on the saturated liquid line. Well, let's take a look at why this works so well. So this is a PV diagram, but this PV diagram is made using actual data. It's actually the data right out of the back of your textbook plotted. So this is drawn to scale. So this is for water. This is our saturated liquid line. Critical point is up there. This is our saturated vapor line. And just as an example, I've drawn a line of constant temperature on here at 200 degrees C. So we can see we have in the vapor region, it follows down along like this, cuts straight across the liquid vapor region, and then goes up in the liquid region. Now, The reason that I've plotted this to scale is to show you if our actual conditions are right here, so clearly in the liquid region, we can approximate the properties at that location by the properties at this location. And the reason we can do that is this is almost a perfectly vertical line. So if we're going to talk about specific volume, for instance, we're saying that the specific volume at that point, V, is very, very close to VF, because the specific volume of this point is that, and because that point is almost directly above this one, the specific volume here and here are almost exactly the same. Now that turns out to be true for other properties as well. The internal energy at this point is almost exactly the same as the internal energy at this point. So we can use the properties along this saturated liquid line here to approximate, and it's a very good approximation, the properties in the liquid region. Now we have to make sure though, when we look up these values of UF and VF or whatever property we need, that we pay attention to the temperature. We need to look up the properties at the right temperature. So that's a way we can get properties in the liquid region. Now let's take a look at an example and just see how these numbers work out. Let's say that we have water and we're given a pressure and a temperature. So the pressure is 25 megapascals and the temperature is 200 degrees C. Well, that happens to be the temperature that I had on this PV diagram, so we'll go back to it. So we have a temperature of 200 degrees C and a pressure of 25 megapascals. Well, this is actually in bar, so we need to realize that 25 megapascals is 250 bar. Okay, so 25 megapascals is 250 bar. Well, 25 megapascals and 250 bar is this blue dot that I plotted here. So this pressure here is 250 and it's on a line of constant temperature, the red line at 200 degrees C. So that blue dot is 25 megapascals, 200 degrees C, the point we're interested in. So first of all, we want to show how we can tell that this is a liquid to begin with. So if we go to this temperature, 200 degrees C, and look up the saturation pressure, we find it's only 1.554 megapascals, which is 15.54 bar. Well, if we go back to our PV diagram, that corresponds to this. So this pressure right here, so 200 degrees C, the saturation pressure is 15 bar. So that's what that is. So we're at a higher pressure than that. In other words, we're somewhere along this line, so that's how we tell we have a compressed liquid. So that's all fine. Now, so we know it's a compressed liquid, so we want to compare these two options for finding the properties of that compressed liquid. The first option would be go to table A5, which is a specialized compressed liquid table. And if we go to table A5, we can look up properties at 25 megapascals and 200 degrees C, and that's what we would find. So those are certainly the most accurate values that we have available. However, if we were to go instead to table A2, which is a saturation table, it's the temperature table, and look at 200 degrees C and look up the values of VF, UF, and HF, we would find that they are very close to these compressed liquid values. So the specific volume is within 2%, it's about 1.9% high. The internal energy also about 1.9% high, and the enthalpy is about 1.2% low. So these are actually quite accurate estimates of all three of these properties at 25 megapascals and 200 degrees C. So the reason that this is happening, just to go back here, is that the properties at this point and at this point are almost exactly the same. Now, why then would we ever use compressed liquid tables? Well, the answer to that is that if we go far enough up here, this line starts to drift off of vertical. So this approximation of these as being vertical lines is really quite good, but we can't take it to too much of an extreme. So you'll find that table A5, which is a specialized table for compressed liquids, only starts at very high pressures. In fact, it starts 25 bar and above. Okay, so 25 bar is where table A5 starts, and it gives data for pressures higher than 25 bar. Below 25 bar, these lines are really almost perfectly vertical, and we can just use the saturation information.